So last time we learned how to solve simultaneous linear equations graphically. Now let's learn how to do it algebraically. It's essentially the same idea, but doing it algebraically instead of doing it graphically. So let me remind you of what we were doing. So we had our axes. So let me draw our axes. And we had two equations, maybe a yellow line and maybe a red line. And they would intersect at a point. This would be the point right over here where they intersected, and this is what we were looking for. So this point I would like to call, this would be x naught, and this height would be y naught. So this point, which is really important for us, this point right over here is x naught, y naught, and this point simultaneously satisfies the two equations. Remember, we had two equations, and this is what we were looking for, the points of intersection. So now let's look at, for example, two equations. Let's look at an equation like maybe 3x plus 2y is equal to 8, and there's another equation 4x minus y is equal to 7. Okay, so this could represent, maybe it doesn't, I haven't drawn it to scale, but this could represent maybe the yellow line, and this could represent maybe the red line, right? So we're looking for a point that simultaneously satisfies both equation 1 and equation 2. That's why it lies at the point of intersection. That's what we did when we did things graphically. So now let's look for that point that simultaneously satisfies both points. Let's call that point x naught, y naught. So clearly that point is going to be 3x naught plus 2y naught will be equal to 8 because it satisfies the first equation. But it also has to be true that 4x naught minus y naught will be equal to 7. Okay? Now we have to make sure that x naught and y naught is such a point that satisfies both these equations. So let's assume that x naught, y naught satisfies both these equations, and let's try to find out what x naught and y naught is. So now you can see that here I have a coefficient of 2, and here I'm just going to put in a 1, and here I have a coefficient of minus 1. So what I can do is I can multiply the second equation by 2. If I multiply the second equation by 2, I'll get a minus 2y naught, and then I can add the two equations and I can get something useful. So what I do is I'll show it to you. I'm going to multiply, so this is equation 1, this is equation 2, and I'm going to multiply equation 2 by 2. So let's write it out. So now you can see that the first equation is still going to be 3x naught plus 2y naught is equal to 8. But the second equation is going to become, I've multiplied the equation by 2, so everything is going to increase by a factor of 2. So I'm going to get 8x naught minus 2y naught is equal to 14, right? So now I can add these two equations, because you see, if there are two equalities, and if I add two equalities, then I maintain an equality. So I can add the two equations. So if I add the two equations, what do I get? I get 11x naught. The 2y naught cancels with the minus 2y naught, so you get a 0, and then I get a 22 on the right hand side, which implies that x naught is equal to 2, and then I can put the value of x naught in any one of the equations. Let's say I put it in equation 1. So equation 1 would imply, you can just figure it out, that y naught, so because 2y naught will be equal to 8 minus 3x naught. 3x naught is 6, so it's 8 minus 6, which is 2. So that means that y naught is going to be equal to 1. So we've just figured out that x naught equal to 2 and y naught equal to 1 satisfy both equations. And you can check. Let's put in the value in equation 1. If I put in the value in equation 1, what is 3x naught? Well, that's 6. What's 2y naught? Which is 2. 6 plus 2 is equal to 8. So equation 1 is satisfied. Let's look at the second equation. What's 4x naught? Well, 4x naught is 8. 8 minus y naught is 1. So 8 minus 1, which is 7. So the second equation is also satisfied. So x naught equal to 2 and y naught equal to 1 simultaneously satisfies the two equations. Now, this is one way to solve the problem. So what we did was, the big picture was that we looked at the two equations. We wanted to find a point that satisfied both equations. So we looked at the two equations and we tried, because you see there are two variables here, x naught and y naught. So we want to get rid of one variable so that we can get an equation which is only in one variable. You see, at the end of the day, we got an equation which was only in terms of x naught. We could have gotten an equation in terms of y naught also, right? So, but you want an equation which is only in terms of one variable so that you can solve it for a value of x naught. We got a value of x naught because we just had some x naughts equal to a number, so we figured out what x naught was. So we want to get rid of y naught. Sometimes you can get rid of y naught, sometimes you can get rid of x naught, but you can get rid of either one of the two so that you can find the value of x naught or y naught and then use that value of x naught to find the appropriate value of y naught. Okay? That's one way to think about it. The moral of the story stays the same. We still want to find the unique point x naught, y naught, in general unique. Otherwise, these are going to be overlapping lines, as we discussed earlier. So in general, the unique point x naught, y naught that simultaneously satisfies both the equations. So this could be one way that you do it, in which you try to figure out how are you going to work with these coefficients so that you can cancel them, right? So we multiplied equation 2 by 2 so that when 2y naught minus 2y naught goes to 0. We could have also multiplied equation 1 by, let's say there's another way to do it. We could have multiplied equation 1 by maybe 4, and we could have multiplied this equation by 3. So we would have gotten 12 x naughts here, and then we could have subtracted the two equations. So the 12 x naughts would have cancelled, and we would have gotten a y naught, an equation only in y naught, and that would have been, we could have solved it for y naught. Okay. So, but you could do it in a slightly different way too. So let me show you another way to do it. The idea would be the same. So let's say you have an equation like, maybe let's pick another equation. Let's say 3x plus 2y is equal to 7. And we have an equation 9x plus 8y is equal to 22. Okay. So we could sort of do it in two ways. So let's do it in another way, and that's called the substitution method. The name is not important, but let's look at the idea. What's the idea? Well, the idea is that we know that we want an x naught, y naught that satisfies both of these equations. We want x naught, y naught to satisfy both of these equations. That's what we're looking for. So now we know that so let's assume that there is such an x naught. So 3x naught plus 2y naught is equal to 7. And we also have 9x naught plus 8y naught is equal to 22, right? And now we can figure out what y naught is. So let's look at what y naught is. We can figure out what y naught is. So from this equation, y naught turns out to be equal to 7 minus 3x naught over 2, right? So now what we can do is we can plug in this value of y naught into this equation. So let's do that. So I have 9x naught plus 8 multiplied by y naught, but y naught is going to be 7 minus 3x naught over 2 is equal to 22. So I can just expand it out. I'm just multiplying. So it's going to be 9x naught. The 8 and the 2 will cancel, so I'll get a 4. So I can cancel so remember, I can cancel this. I'll get a 4. So I'm going to get 4 7 is 28. 28 minus 12x naught is equal to 22, which implies that 28 minus 2, which is 6. So I'm going to get 6 is going to be equal to 3x naught, which implies x naught is equal to 2. And now I can, since I know x naught is equal to 2, I can use this expression for y naught. So this implies that y naught is equal to 7 minus 3x naught, but 3x naught is 6. So 7 minus 6, which is 1, so it is just equal to 1 over 2, right? So here's another way that we could solve it, and both ways are equally valid, right? Okay, so just to make sure that you understand, we could have done this problem using the previous method, which was multiplying and getting the two equations to be the same. So let's do it. Let me write it out again. So let's do it using the older method, which is, I guess, called some simultaneous method or something, whatever it's called. So let's look at this one. So I have 3x plus 2y is equal to 7. So let's look at 3x plus 2y is equal to 7. 3x plus 2y is equal to 7. And I'm putting the knots here because that's what I actually want for the simultaneous solution. And I also have 9x naught plus 8y naught is equal to 22. So now let's say I want to get rid of the x's this time. So let's get rid of the x's. So now you can see this is a 3x naught and this is a 9x naught. So I can multiply. So let's say this is equation 1 and this is equation 2. So what I can do is I can multiply this equation by 3. So if I multiply this equation by 3, I'm going to get a 9x naught plus 6y naught is equal to 21. And I still have, for the second equation, I still have the same things. 8y naught is equal to 22. And I can subtract. So if I subtract 9x naught from 9x naught, I get a 0. So I'm going to subtract. So if I subtract 9x naught from 9x naught, I get a 0. 6y naught minus 8y naught is going to be equal to minus 2y naught. And 21 minus 22 is equal to minus 1. So this would imply that y naught is equal to a half. So if I put in y naught equal to half, so I can put it in any equation. Let me put it back in equation 1. So if I put it back in equation 1, that's equal to 3x naught plus 2y naught. But 2 times a half is 1. So that's just equal to 1 is equal to 7. So I'm using this equation, which implies that 3x naught is equal to 6, which implies x naught is equal to 2. So now we have the same solution as we had previously. X naught is equal to 2, y naught is equal to half. X naught is equal to 2, y naught is equal to half. You could do it either way and you get the same answer. Okay, so there's no magic here. It's fairly straightforward, fairly simple. You just have to do the algebra right and your arithmetic right. Okay, and to sort of sometimes people to confuse you can make some silly little changes. So let's look at, so if you get an equation which looks like this, x plus 1 over y plus 2 is equal to 1 over 2, and there's another equation which looks like x minus 2. Maybe I should write it out here. And I can write it out as, there's another equation which says x minus 1, x minus 2 over y minus 1 is equal to a third. So what we can do is we can just cross multiply. So if I cross multiply, this becomes just 2x plus 2 is equal to y plus 2, which is really the equation 2x is equal to y. And that's really straightforward. And this equation becomes, if I cross multiply, I'm going to get 3x minus 6 is equal to y minus 1, which really is the equation 3x minus y is equal to 5. So I have these two equations. This is equation 1, this is equation 2, and I can solve it using any method that I want. Okay, so if I give you a problem which looks like this, it's not really a different problem. It's really the same old problem with a slightly different guise. So there's nothing of particular interest here. The only thing that I want you to understand is that when I started out, these were equations, right? So I had an x and a y here in general, right? And if you go back, I can go and look at this one. These were also equations. Equations are functions, right? Once I switched from so equation 1 represented a function, equation 2 represented a function, the lines that we drew. But when we move to a particular point, so that's the only thing that I want to emphasize, we moved from here to over here. And what we did was we said there's a particular point, x naught, y naught, that simultaneously satisfies both of these equations. So now they are no longer general equations of curves. When I put in an x naught, y naught, I'm talking about a particular point that satisfies these equations. So that's the only little slight change that I make. In general, people don't do it. They just continue working with the x's. So what in general people do is, let me go to the next page, which is slightly cleaner. They don't actually bother with the x naughts. So they actually don't bother with the x naughts, and they actually work with just the x's, And that's the usual way that people work. I just wanted to make sure that you understand how people in general work. So they get the answer x is equal to 2 and y is equal to half. And that's what people do because they don't actually differentiate between the point and the function. I was just being a bit more careful and I was trying to differentiate between the point and the function. But in general, it's not done. It's not the usual practice, and people just work with x and y's, and they confuse the x and y point with the x and y, which represents a general functional relation that is captured by the line. Okay, thank you.